Hello, everyone. Welcome to another wonderful day of chemistry. So far this semester, we've been zooming out and trying to build a more accurate version of a bonding model. So we went from Lewis theory to Vesper to valence bond theory, improving all the way. Today, we go ahead and we actually look at the real story, and that's molecular orbital theory, which tries to encapsulate all of the nuance that is quantum mechanical features into a real story of bonding. So valence bond theory is really good as it gives us a sketch of how our orbitals come together. However, it doesn't really quite show how all of the atomic orbitals can combine to make a full molecule. It tends to be looking at an individual bond at a time. So if we want a really good view of how two atoms can make a simple molecule, for that, we're really going to need to be looking at our molecular orbitals. I'm trying to bring in some of the missing parts of this story. So let's go ahead and start with one of the simplest molecules we can. That's the hydrogen molecule. It's two atoms, two electrons mixing together. So we know that our hydrogen molecule will be made of two atoms, each with a single electron and a single 1s orbital. Now these two can go ahead and mix together to make a sigma orbital, which we've seen with valence bond theory. The two orbitals overlap. We have an increased density in between the two atoms. And it's this increased density in between the two atoms which pulls the two electrons together. However, we have two orbitals that are mixing. And one of the things we saw a little bit with valence bond theory is however many orbitals we have come in, that's how many orbitals we should produce. So if something goes down in energy and becomes more favorable, something else has to go up and become less favorable. And so whenever we produce a bonding orbital, we also produce an anti-bonding orbital. So a good way to think about it is when we make a bonding orbital, it's all the best parts of these two orbitals that make the most stable molecule. The anti-bonding is the leftovers. It's everything that makes this bond unstable. So as downhill in energy as the bonding orbital goes, the anti-bonding orbital will go at least that far up in energy. And as a result, what ends up happening is I deplete all of the electron density in between the two atoms. So all of the electron density is going to be on the outside. And as a net result, what ends up happening is that if I start occupying this anti-bonding orbital, it starts pulling the molecule apart. However, for most of our cases, that isn't a real problem. So let's look at hydrogen. It's got two electrons, one in each of our starting orbitals, which means that those two electrons, according to the Pauli principle, can all go into that bonding orbital, and we're happy. This makes a nice molecule. I've filled up my orbital that pulls my two atoms together. Now, let's see what happens if I go to helium. So if I have two helium atoms that come together, now I have to add two more electrons to this diagram. Ruh-roh-roarge, because those two electrons went into the anti-bonding orbital. So the bonding orbital is pulling the two atoms up together. The anti-bonding is pulling the two atoms apart. So now I have just as many atoms trying to pull the molecule together as I have electrons trying to pull the atom apart. And as a net result, there's no net force trying to bring these two atoms together. And if there's nothing saying one way or another, more or less what happens is, like so many relationships, if there's nothing pulling you together, you tend to drift apart. And this is exactly what tends to happen in systems. So if we have just as many electrons destabilizing the bond as stabilizing, the system no longer sticks together. And we can actually kind of quantify this with a more numeric version of something we've talked about before, and that's bond order. So when we talk about single bond, double bond, triple bond, one of the things we're really looking at is a measure of how many electrons are tying the system together. And so far what we said is if I've got two electrons tying the system together, that's a single bond. Four electrons, that's a double bond. And we're just going to quantify this in an MO sort of way. We're going to count up all of the electrons in a bonding orbital minus all of the electrons in an anti-bonding orbital. How many are pulling me together minus how many are pulling me apart. And then to turn it from electrons to bonds, I just divide it by 2. So if I look at H2 plus, I've got a single electron tying together two hydrogen atoms. Well, one together, none pulling. This is a half bond order. So it's not exactly the most stable molecule. So if I try and remove a electron from H2, not so good. Now, if I look at H2, I've got two electrons pulling my system together, none pulling it apart. So I've got a bond order of 1. This is a single bond. This is kind of our bread and butter of molecular theory. Now, we can either add in an electron to make H2 minus, or we can imagine taking helium and removing an electron to make H2 plus. Either one of these will be isodegenerate or isotopic. The major idea here is that they have the same electronic structure. Now, in this case, we've got two electrons pulling us together and one pulling apart. So 2 minus 1, 1. I've got a bond order of 1/2, which means this is just as stable as H2 plus. So by putting an extra electron into the system, it turns out I actually destabilize the system because those electrons, there's no more room to bring these atoms together. So if you add any more of my glue, it just starts falling apart, like some of my craft projects. It happens sometimes. And if you add in that extra electron to make diatomic helium, now I have just as many electrons together as apart. I have a bond order of 0. And the general rule here is the higher the bond order, the more stable the molecule, the more I have holding the system together. However, if I have a low bond order like 0, this means that my atoms are gonna tend to drift apart, no bond present, and I've got 2 free atoms, which is the reason why you will never see diatomic helium. Because with a bond order of 0, there's nothing there. Now, it turns out we can apply this same logic to second row elements. Unfortunately, when we have second row elements, we now have to look at how p orbitals combine. And we've already seen this to a certain extent, because my p orbitals can either overlap to form a sigma bonding orbital, where I have all of the good things in the middle, or they can make a sigma anti-bonding orbital, where I have all the bad things together. So in the bonding, I've got all this electron density pulling the system together. In the anti-bonding, I have all this electron density pulling the system apart. Now, if this works for sigma, it turns out it also works for pi. So as we've seen before, you can combine 2 p orbitals, and this will make a pi bonding orbital. However, what we're neglecting is that there's also some density in our p orbitals that aren't in between the 2 atoms. We have this density out here and this density out there. And if I mix these 2 together, I can also get an anti-bonding orbital. Remember, 2 orbitals in, 2 orbitals out. You get a bonding and anti-bonding. This one is very favorable. This one, not so much. And if this works in the z direction, it'll also work in the y direction. So you can either, since we are going to be bringing into, since we have a grand total of each atom providing 3 p orbitals, one of those will form a sigma, and the other 2 will form these pi bonds as they're pointing in the opposite direction. Now let's go ahead and look at the energetics for this. Now, if I've got any atom larger than oxygen, we have a fairly simple sort of idea here. My s orbitals will mix just like in hydrogen. I'll make a sigma bonding and a sigma anti-bonding from those s orbitals. Electron density between, electron density pulling apart. And we have the same thing with the p orbitals. And with the sigma p orbitals, one goes down, the other one equally goes up. And in general, as we saw, there's a lot of good overlap when I make that bonding orbital, which means there's a lot of bad overlap in the anti-bonding orbital. So my highest energy orbital is going to be the sigma anti-bonding, and my lowest of the p mixing is going to be that sigma bonding. And the pi orbitals more or less end up in between. Now, let's say I've got some electrons to put in here. So my first 2 electrons will go in the lowest energy orbital. So I'll go ahead and put them in my s orbitals for the individual atoms. Then those 2 electrons, as the 2 atoms mix, will go into the lowest energy molecular orbital, or that sigma bonding. If I add 2 more electrons, they go into the sigma antibonding. If I add 2 more electrons, well, now I'm starting to occupy my p orbitals in my atomic orbital system, and this makes my sigma bonding from my p orbitals. Add in an extra 2 electrons, and I start filling that pi shell. And with a total of 5 electrons, I've now completely filled that pi shell. Extra electrons now go into the antibonding, fill it up with the next 2. Finally, if I have a full 8 electrons in my atomic orbitals, this means I've completely filled my molecular orbitals, and I have just as many electrons pulling the system together as pulling apart. Now let's go ahead and try and look at what these orbitals look like in kind of a 3-dimensional space. And one of the big things I want to kind of point out is that once I go to this second row, what ends up happening is the distance in between my 1s orbitals means that there's very little interaction overlap in between the 2. And as a result, it turns out my core electrons don't really have any contribution to bonding. And so we typically won't talk about the core electrons at all, even in MO theory, because they tend to stay fairly separate and they will be completely filled up. So it's a guarantee they will have just as much bonding as anti-bonding character from those core electrons. Now, if I start adding in more electrons, they'll start filling up these sigma s orbital bonding and anti-bonding. And if I'm talking about anything after beryllium, so boron and afterwards, I will also have enough electrons to fill both the bonding and anti-bonding s shells. And as a result, most of the time, if I'm looking at boron and forward, turns out my 2s orbitals also aren't going to have a lot of impact. There will be equally as attractive as repulsive in these diatomic sort of systems. Now, if I start bringing in other molecules, more than just simply the 2 mixing, that won't necessarily be the case. But for these diatomic cases, they tend to cancel out. So most of the interest is going to be put on these p orbitals, as this is where most of the action is. However, there is one last little thing we have to worry about, is that the contribution of these s orbitals isn't over with. Because you'll notice that this sigma p orbital actually is pretty similar in energy and kind of picture to those s orbitals. And it turns out that these p and s orbitals can start to mix. And they tend to mix the most when their energies are fairly close. And it turns out their energies are going to be fairly close if I've got a lower nuclear charge. Because as I have a lower nuclear charge, I haven't essentially split apart the orbital energies of these systems. Because remember, as I put in more electrons into my atomic orbitals, the difference in between p and s energies became greater and greater and greater because of shielding. And that has a very important fact on here, because if these orbitals get close enough in energy, they mix a lot. And it turns out that this sigma p doesn't like handing out with this anti-bonding s orbital. And so if I've got any element that's lighter than oxygen, so think about boron, carbon, nitrogen, as well as lithium and beryllium, what ends up happening is this sigma p orbital runs desperately away from my anti-bonding s orbital. And it runs so far away, it becomes higher in energy than those pi bonds. And this has some real important contributions to what we'd expect to see out of bond order and electron filling. So let's go ahead and walk through our diatomics. So when I'm looking at lithium, or diatomic lithium, it's fairly straightforward because I only have my sigma bonding orbitals. I get 2 more electrons and I have equally sigma bonding and anti-bonding. So don't really expect to see much diatomic beryllium because, well, it turns out it has a bond order of 0. Then I go to boron and I start occupying that pi shell because it's lower than that sigma, which is still desperately running away. Carbon now completely fills that pi shell, and then I get a little bit more electrons in nitrogen, and now I've filled both pi and sigma. However, as soon as I get to oxygen, something very significant happens, because now those sigma orbitals are lower than the pi orbitals. This doesn't have any real consequence because they'll all be filled anyways. But in terms of molecular interactions and what complexes nitrogen and oxygen form with other molecules, it can become very important because where those highest energy orbitals are has changed. And then for oxygen, now I'm starting to occupy my anti-bonding pi orbitals. And by the time I get to fluorine, I have completely filled that pi anti-bonding shell. And so this actually is a very important thing to remember, is we will have a slightly different orbital configuration for nitrogen and lower versus oxygen and higher. I tend to like remembering the oxygen and higher configuration because that way we have a constant pattern. The bonding orbitals go down in energy as much as the anti-bonding orbitals go high. And this gives a very symmetric pattern. And then just remember, we have this fleeing action for nitrogen and lighter. Now, once we have these orbital diagrams, we can use these to determine the bond order for very specific diatomic species. So let's go ahead and start by looking at oxygen. Oxygen has that nice symmetric orbital diagram. And as I said before, it has its 12 valence electrons, which means we've completely filled up the s bonding and anti-bonding, my sigma p bonding, my pi p bonding, and I've got 2 electrons sitting in my pi anti-bonding. Now, in order to determine our bond order, let's go ahead and count up how many electrons are holding my system together. So I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals, and 1, 2, 3, 4 electrons in anti-bonding orbitals. So 8 minus 4 divided by 2, I've got a bond order of 2. So this actually works with what we tend to think about. Oxygen is connected by a double bond. In addition, MO theory also tells us that oxygen is paramagnetic, because note that we have these parallel spins for oxygen, for these 2 valence shell electrons. And this means that it turns out molecular oxygen can respond to magnetic forces. And this is a tool that is sometimes used in chemistry. Now let's go ahead and look at nitrogen. Important thing to remember for nitrogen is that sigma bonding orbital is going to be higher in energy than that pi bonding orbital. And from here, we can go ahead and fill up our diagram. And let's go ahead and count our bonding orbitals. Well, we have all the same bonding electrons as we did in oxygen. Only difference is now I'm missing 2 anti-bonding electrons. So I'll have 8 minus 2. This gives me a bond order of 3. Nitrogen is held together by a triple bond. This agrees with our Lewis theory and actually explains where the Lewis theory comes from. We have both sigma and pi bonds holding the system together. However, this also illustrates that you will never get that quadruple bond that Lewis theory would tell you you'd get for carbon. Instead, what we can do is look at the bond order for all of our various molecules. So for lithium, it will be only have a bond order of 1 and will be diamagnetic. Boron, however, beryllium will have a bond order of 0, boron, bond order of 1. But notice now we have unpaired electrons, so it will be paramagnetic or it will respond to a magnetic field. Carbon has a bond order of 2, not the 4 you'd expect from Lewis theory. And so you have to actually pull some clever tricks to get a bond order of 3. Mostly you have to find a way to coax away these anti-bonding electrons into, say, a carbon-carbon bond or a carbon-hydrogen bond, like we see with alkynes. And then when we get to nitrogen, it can get that full triple bond with everybody paired up, so no response to a magnetic field. Oxygen, even though I threw more electrons into the system, which you'd assume would allow the bonds to be closer, Instead, these electrons start tearing apart the system, and I have a bond order of 2, and that paramagnetic field. Fluorine, even though the system is chock full of electrons, now I fully am tearing the system apart, and all I've got holding on the system is a single sigma bond. And by the time you get to neon, well, turns out there's a reason you don't see diatomic neon. There's just too many electrons to allow this system to come together. It naturally will pull itself apart. Now, this is actually a pretty good and accurate way to look at things like a pretty good and accurate way to look at diatomic molecules, especially homonuclear diatomic. However, things get a little bit messier when I have two different atoms coming together in what we call a heteronuclear or different nuclei molecular bond, or if I'm trying to make a full molecular species. So we'll take a quick look at those species next time. Until then, take care.